Okay, today we are on our sixth week of quarter four. Our today's topic is graphing logarithmic functions. Before that, I want to bring to your attention one general knowledge. Do you know the tallest buildings in the world? The first one is Burj Khalifa at the left of Dubai City of United Arab Emirates, which is 2,717 feet divided across with 163 floors. The One World Trade Center at right in New York City is sixth in the world. That is really Dubai is one of the fastest growing cities in the world. If you get chance, if you visit, that would be great. Okay, let's go to today's lesson, which is graphing logarithmic functions. We need to remember logarithmic and exponential functions are inverse of each other. When we say inverse, inverse functions or relations have different properties. The first property is that inverses undo each other. Say we can solve exponential equations using log functions. That's the first property. The second property is inverse relations are obtained by switching the coordinates of the original relation. This means if xy belongs, say, to the function f, say the exponential function, then point yx will belong to the inverse, which we write as f negative 1, say to the logarithmic function. So these are the two first properties of inverses and their function. The third property is always the range of a function is the domain for its inverse, and the range of the inverse will be the domain for the original function. Having said this, how are we graphing logarithmic functions? I will demonstrate this with different examples. Okay. Suppose we want to graph, as an example, we want to graph y equals log x to the base 2. So step 1 is rewrite it in terms of its inverse. So I know y equals log base 2 of x. In the last 2 weeks, you learned that how to rewrite this is 2 to the power of y is x. But since we want it to be in terms of function, we switch y and x because we can't write functions in terms of x equals. So usually what we do is y equals 2 to the power of x. What I did is I replaced this x by y, that y by x. I switched. So this is the actual inverse function. Inverse of y equals log base 2 of x. So in general, y equals log base a of x, if you have, has inverse y equals a to the power of x. Its inverse will be just y equals a to the power of x. Now if we want to graph that, let's go to graphing this. What I do is I create a table for y equals to the power of x, which is x, say y. So I take few points. Suppose if I take negative 1, to the power of negative 1 is 1/2. You remember that. When x is 0, it will be 1, to the power of 0 is 1. When x is 1, it will be 2. When x is 2, it will be 4. Okay, so if I want to graph log base 2 of x, what I do is just I switch these values, half, then negative 1, 1 and 0, and 2 and 1, and 4 and 2. I'm just switching those. Now I'm graphing the graph. Let's go here. Suppose if this is 2, this is 4, 6, -2. I can go on y-axis with different scaling. Say I can go with 1, 2, and then so when x is half, this is 1. When x is half, okay. Suppose this -1, -2. When x is half, 1 is here, half is here, y is -1. So I have that mark. When x is 1, it is 0. When x is 2, it is 1. When x is 4, it is 2. So this would be the graph of y equals log base 2 of x. Okay, so now if you take y equals to the power of x, you can graph it. In fact, when -1, it is half here. When x is 0, it is 1. When x is 2, for instance, it is 4. But when x is 1, it is 2. So anyway, this was the graph of y equals 2 to the power of x. Okay. Domain for y equals 2 to the power of x and y equals log x to the base 2. The domain for this is the set of all x. Say that x er. But the domain for this is all x greater than 0 for the log function. The range would be, for this one, the range is y. Say that y is greater than 0. As you see it, the domain of the range of the 2 to the power of x would be in the domain of the inverse. And here, the range for the log function is the set of all y. Say that y is an element of R. Okay, which was the domain for the exponential function is now the range for logarithmic, which was the range for logarithmic would be, which was the range for exponential would be the range for logarithmic. If we see y-intercept, for this, the y-intercept is 0, 1. For this, none. It doesn't have y-intercept. The x-intercept for the horizontal, for the exponential, it is none. But the logarithmic has 1, 0, which is 0. Vertical asymptote. If you see the properties or the basic features of these graphs, vertical asymptote, none for the exponential. It doesn't have vertical asymptote, but this one has vertical asymptote, x equal to 0. X equal to 0. Horizontal asymptote. This one has y equal to 0, which is 2 to the power of x. Has y equal to 0, the x-axis, this one. But the logarithmic function doesn't have no horizontal asymptote. Okay. Now let's take another example where we can graph logarithmic function. Example 2. Graph y equals log base half of x. What you do is, as we said, you take y equals half to the power of x is the inverse of this. So you take that value, which is when x is, say, if it is -1, it will be 2. If x is 0, it will be half When x is 1, it will be half. When x is 0, it is 1. Sorry, just 1. Because half to the power of 0 is 1. When it is 1, it will be half. And when x is 2, it will be 1 over 4. So if you want to graph y equals log base half of x, you are switching these values, x and y. 2, negative 1, 1, 0, half, 1, and that 1, 1 over 4, and 2. Okay. So what we do is we take just the values here, and then this is say 2, this is 4 and 6. As usual, with different unit here, it's okay. Take that, and then when x is 2, it is negative 1. X is 2, it is negative 1 here. When x is 1, it is 0, just there. When x is half, it is 1. When it is 1 over 4, it is 2. It gets closer to that. Still, the domain and range of this function will be the same as what we had earlier, and the x-intercept is at 1, 0 anyway. So the same way, likewise, to graph log base x, y equals log x, which is common logarithm, use y equals 10 to the power of x, so the table of values of 10 to the power of x. To graph, if you want log base e of x, which is or y equals ln x, the natural logarithm, use y equals e to the power of x. So just it's about reversing the possible coordinates of those functions. Having said this, we go to how we do transformations of functions, or especially transformation of logarithmic functions. I want to bring to your attention some properties or rules of transformation, which is how can we do reflection and translation at least. If you remember, when x is replaced by negative x, say y equals f of negative x, this is reflection across the y-axis. You remember that. When y is replaced by negative y, say if you have y equals negative f of x, that will be a reflection across the x-axis. Say log of negative x is a reflection of log x, y equals log x across the y-axis, but y equals negative ln x is the reflection of y equals ln x across the x-axis. You can see this with the following graph. Yeah. Y equals log x, y equals log negative x, reflection across y. Y equals log e base e of x, y equals negative log e of x across the x-axis. Okay. Other properties of translations. You remember when you replace x by x plus c, it is a shift to the left. But if you replace x by x minus c, it is a shift to the right by c units. So our function f of x plus k means shift up by k units, of x minus k is shift down. So I'll demonstrate this in terms of logarithmic functions. Okay. Let's graph, for instance, examples. We can see different examples. Graph y equals log x plus 2. If I take this function, this is a shift to the left by 2 units of the original function y equals log x. So this logarithm to the base 10. I know how to graph logarithm to the base 10. For instance, I mean the inverse is where inverse is y equals 10 to the power of x. Okay, so if I want to graph log x, I graph xy or y equals 10 to the power of x first. When it is negative 1, say it is 1 over 10. When it is 0, it is 10. When it is 1, it is, when it is 0, it is 1, always 10 to the power of 0 is 1. When it is 1, it is 10. Okay, you should remember that any number to the power of 0 is just 1. Okay, so if you want to graph logarithm y equals log x, as we said, we are switching the x and y. 1 over 10 goes to negative 1. 0 or 1 goes to 0, and 10 goes to 1. Okay, so for instance, if we have this 2, 4, 6, 8, and 10. Suppose if I want to graph log of x, y equals log x plus 2, I should graph first y equals log x, which is when it is 1 over 10, it is negative 1. If negative 1, positive 1, 2, 3, say. When it is 1 over 10, closer to this, is here. When it is 1, it is 0 there. When it is 10, it is 1. So this is my original function, or the parent function. This is 10 comma 1. This is 1 comma 0. This is 1 over 10 negative 1. Okay, so if I want to graph log of x plus 2, I'm moving this to the left. Just this 1, 0 comes to negative 1, from 1 to negative 1. The 10, 1 comes to 8, 1 here. This 1 over 10 goes to 2 units, which is 1 over 10 to 9 over 10, 1, and closer to negative 2, 2 units. If you go, it would be just 1, negative 1, and 9 tenths there. So the graph would be just this one when it moves 2 units to the left. So likewise, if I want to graph y equals log x minus 2, say, this is a shift to the right, by 2 units, because it's x minus 2, by 2 units. So I'm just shifting this 2 units to the right, meaning the 110 becomes here 310. The 10, 1 becomes 10, 12, 1 here, units. So the 1 over 10 becomes here to 9 over 10. 1 and 1 over 10, and then 2 and 1 over 10, or from 1 over 10, if I move 2 units, 1 and 1 over 10, 2 and 1 over 10, just around here. Okay, so this is it. Moving up or down is the same way. You are just moving these points up or down. But for instance, the vertical asymptote also moves. Vertical asymptotes say for y equals log x is x equal to 0. X equal to 0. Vertical asymptote of y equals log x plus 2 is this vertical asymptote 0 moves 2 units to the left, so the vertical asymptote will be here on negative 2. Is x equals negative 2. Vertical asymptote of y equals log x minus 2 is, because since this 0 equals 2 is moving 2 units to the right, it will be just, use same color. So this would be the vertical asymptote for that, which is x equals 2. So this is y equals log x minus 2. This is y equals log x plus 2, which goes to the left. If I'm graphing up, say y equals log x plus 2. This is a shift up by 2 units. Look, this is not in parentheses, x plus, you are adding on the whole function when you are shifting up. The same way, y equals log x minus 2 is a shift down. A shift down by 2 units. Okay, so this is all about how to graph logarithmic functions, including their transformation for this week. Thank you.